Okay. Hello, everyone. Welcome to episode 27 of Warsaw Quantum Computing Group meetup. Today we host a great guest from Alexandria Quantum Computing Group, Professor Ahmed Younes. So thank you very much, Professor, for accepting our invitation. And the title of the lecture is Applications of Using Partial Negation Operator on a Single Qubit. So it sounds very interesting. So we'll start the lecture soon. The meeting is recorded, so it will be later available to all registered people. And if someone has any questions, then please you can interrupt during the lecture. So this is information from Professor Ahmed. And I believe that he will also explain it later. And just in case, you can also post your questions on chat, so we can ask your questions at the end during the Q&A session. So before we start, I would also like to thank our partners, our strategic partners who support us, like Snart or Codec, and our honorary patrons. So Alexandria Quantum Computing Group is also among our honorary patrons. So we are also very happy that the group of Professor Ahmed Younes also supports our activities. All right, so I think we can start. So I will just stop sharing my slides. And Professor Ahmed, the Zoom is yours, so you can start sharing your slides. Okay, we can see.
Hello, everyone. Is my screen available for you now?
Yes, we can see it.
Yeah, okay.
Yeah, we can see it.
Hello, everyone. I'd like to apologize for changing time this time, and I hope you will find my talk useful. It is with title Applications of Using Partial Negation Operator on a Single Qubit. Actually, partial negation operator or negation operator, it is a really simple, really trivial operation, which is taking the root of the usually Pauli X gate. Pauli X gate is the equivalent gate to the NOT, the negation in classical computing. But I mean today by partial negation is that we can actually take an arbitrary root. Square root may be popular in the decomposition of Toffoli gates, square root 2. But today I will deal with the C's root of the X gate. So if we take the C root of this gate, it will take this form. Which t here is the square root of -1, but to c, not to the usually square as we used to do. So actually applying this gate for d times, if we apply it for c times, it is equivalent to the NOT gate. So simply we are just trying to divide the negation not only applying it once, but we can apply negation as a sequence of gates. So if we apply this gate for d times, it will take this form. What's the possible application of such a simple operator? Let's see. Let's start and see with some simple applications and see how useful it can be. First of all, we can just scale the negation, divide the distance from 0 to 1 to an arbitrary scale. For example, just to understand, this is a simulator, Javantam simulator. It is developed in our group, but it is based on another simulator called Jacuzzi. But we did some modifications. It is an open source. We did some modifications on it, so I will use it during the talk. Here, the V on the simulator, we will call it root x6 or root x7 or root x8, whatever the value of C. So what's the effect of applying this simple operator on a single qubit? Here I took the root 6, the sixth root, and I divided it to 6 steps. So applying 6 consecutive roots will actually move the probabilities as follows. So applying once, it will start moving the amplitudes from the 0 to 1. NOT gate will just transfer the amplitudes from 0 to 1 in one step, but using the partial negation, we will start moving from the 0 to 1 gradually until we reach to the full negation. This is the usual negation, but in 6 steps or 7 steps or 3 steps as we want. Is it useful? Actually, this figure may remind you of the grayscale level in image processing, for example. So actually, this might be useful in encoding the gray level in an image. So instead of using a byte in the usual image processing, on quantum image processing, we can use it will be useful to use partial negation to encode the gray level. So we can actually, if we have 256 level, we can route the negation to 256. It is arbitrary. We can do whatever we want. So actually, it can be applied also to the red, green, blue channels. If we want our image, our quantum image, to be colored, so we can use the same concept, but on 3 qubits, because we all know that the red channel can be visualized as a grayscale. So we can actually use 3 qubits to store the information of an image. So this is just a simple example so far. Another interesting example of partial negation is to store data, to store binary data. Let's see what we can do. For example, if we have this binary data, 10101, can we store it on a single qubit? Actually, we can using partial negation, but controlled partial negation this time. Actually, the encoding techniques is very important in machine learning, quantum machine learning, for example. To encode data, to compress data on a single qubit, for example, will be very useful in tasks like this. So in this circuit, first I initialized qubits with this data 10101. And I controlled the partial negation operator with this data. So actually, the amount of negation transferred to the 1 on the auxiliary qubit, on the last qubit, will depend on the binary data. So somehow we can store information on this qubit using partial negation. But let me start to discuss another application, another very useful application, which is reading the content of the single qubit itself using partial negation. How can we do that? Actually, this is one of the challenges we face during designing quantum algorithms, to read the data, the output on a qubit, especially that it is in a superposition. So we know that a qubit in a superposition can take this form, for example, and usually to read the content of this qubit, we apply sharp measurement. Sharp measurement is an irreversible operation where actually the superposition will collapse to either 0 or 1 in a probabilistic way. So if we apply sharp measurement on this qubit, it will collapse to 0 with probability cosine square and 1 and so on. So the question is, can we get any information from that qubit without destroying the superposition? This is paper published 2 years or 3 years ago, and I'd like to discuss it with you and with another applications built on this paper. So let's see what we can do using this very simple partial negation. So the question, the challenge today is to read to know any information about this qubit without applying any sharp measurement on that qubit and without disturbing the superposition, as if we are sneaking to see what's going on the qubit without disturbing the qubit. This has many applications in quantum algorithms, for example. Let's see what we can do. We will show a quantum algorithm where actually we can read the qubit without applying sharp measurement on the qubit. But actually we have to apply sharp measurement, but on an auxiliary qubit weakly entanglement, and we will show what's meant by weakly entanglement in a minute. Actually, if we count the outcomes of the sharp measurement on the auxiliary qubit entangled with the unknown qubit, we can get very useful information. Moreover, we realize that actually the behaviors, the dynamics of the system simulates or very similar to the random walk, and random walk itself is very interesting. Random walk has many applications in computer science and in finance and in medicine and in many fields. So let's see and watch this random walk. The interesting part in this technique is that this weak measurement that we will talk about can be reversed. So it is a reversible operation. So weak measurement today is a reversible operation, not irreversible as usual. Reversible on the unknown qubit, not on the auxiliary. Auxiliary will be destroyed or will be collapsed to one of the classical states, but it can be reversed on the auxiliary on the unknown qubit itself. Also, this weak measurement, the strength of this weak measurement can be controlled as if you adjust the volume of your speaker. You can increase the strength of the measurement or decrease it, increase it to be similar to the sharp measurement, or decrease it to an arbitrary level as you wish. This can be done using this free parameter here, mu. We will show now the importance of this free parameter, which you can change as you wish. You can adjust your algorithm, adjust your measurement process using this mu operator. So let's see how can we do this. We just saw this in a minute. To store this binary information in a single qubit, we can apply controlled partial negation on an auxiliary qubit, but we will define now an operator. We will call it MX, which is a sequence of partial negations followed by sharp measurement, followed by a reset operator, because we will iterate actually this operation. So we want the auxiliary qubit to start in 0 state after each iteration. So if you apply this operator on an auxiliary qubit initialized to state 0, you will get AX, the auxiliary qubit, in this state. D here refers to the number of ones in this vector. So we will call this the one density of the vector. D here is the one density of the vector. So the amount of negation applied on the auxiliary qubit will depend on this D density. What will happen if we want to apply measurement on the auxiliary qubit now? Actually, the probability to find AX using sharp measurement to be in state 0 will take this form, and probability to find one will take this form. I just want you to notice that this D information that was in the vector, the binary vector, it now appears on the probability of the auxiliary qubit. So how can this be useful? The idea is simple. Here is our unknown qubit. We augment the system with n qubits, n dummy qubits, and an auxiliary qubit, and we will apply these controlled partial negations, and we will store everything on the auxiliary qubit. But actually, for our purpose, the algorithm, I will initialize actually everything, and just to show this for illustration. But actually, in the algorithm, I will initialize every dummy qubits to state 1. So actually, the controlled operations here is useless. This will be applied anyway. So the algorithm can be simplified for construction. If you want to simulate it on IBM quantum computer, for example, it can be simplified to this. So this number, and actually this number of V gates now is mu. So you can actually change this number as you wish. So this is the unknown qubit now. This is the auxiliary qubit. We use this controlled V to weakly entangle the unknown qubit with this auxiliary qubit. And I will show in a minute what's the effect of applying these V gates. So this is another simpler form if you don't like to see these all V's on the figure. So this is simply the algorithm. We will iterate everything. So we will iterate a control V followed by mu of the V's, followed by sharp measurement on the auxiliary, followed by the reset operator. So just to illustrate what happens here, just to show equations, and I will not go in details in the mathematics in the paper. You can check, and if you have any questions, I will be happy to answer. So let's visualize the circuit without removing this dummy qubits, just to understand what happens and what's the effect of this mu. So the system here, we have this auxiliary qubit, and this, sorry, this is the unknown qubit, and this is the auxiliary qubit. You can see the mouse, right? The mouse is
yes, we can see.
Okay. So this is the unknown qubit, this is the auxiliary qubit, and this is the sequence of the mu dummy qubits, all initialized to state 1. So this system can be rewritten here. Again, mu is a free parameter, which you'll see is that it will be very useful. Now, when you apply this mx operator on this system, the auxiliary qubit will be transformed from 0 to this state entangled with the psi 0. Psi 0 is the cosine of the unknown qubit, and psi 1 is the sine of the amplitude of the state 1 of the unknown qubit. Let me take your attention that D0 actually is number is equal to mu, and D1 is equal to mu plus 1. Why plus 1? Because of the unknown qubit. So there is difference D1 between D0 and D1. D here is the 1 density of the operator. So the strength or the parameter on the 0 part of the unknown qubit is D0, and equal mu plus 1 for the 1 part of the qubit. Now, if you want to measure the auxiliary qubit, you will find the probabilities of the auxiliary qubit to be in 0 or 1, taking this form, just to take your attention that actually the probabilities in the unknown qubit now appears in the probabilities of AX. What we want to do now, we want actually to read the content, read the information of this unknown qubit. But we don't want to apply any sharp measurement on that qubit. Instead, we can apply sharp measurement on the auxiliary qubit. So we will start counting the outcome, because it will collapse to 0 or 1 after each sharp measurement. We will start to count how many ones and how many zeros appear on after measuring the auxiliary qubit. So let's J0 be the count of AX equal 1, 0, and J1 counts how many times we found AX equal 1. Actually, if you find, after each iteration, if you find AX equals 0, the system or the amplitude of the unknown qubit will be updated. these things we cannot avoid. So it will be updated according to this formula. And if we find AX equal 1, we will find the system as follows. Before going far in this, I'd like to show you a simulation for the system, just to understand what we are trying to do in this algorithm. This is a setup for the algorithm. Here, this is the unknown qubit. This is the auxiliary qubit. Now we entangled the unknown qubit with the auxiliary qubit. Here I use mu equal 11. Mu equal 5. Sorry, mu here equal 5. I can make it 6, 7, 8 as you want. Let's see what will happen. Here I assume that the unknown qubit is the Hadmard actually. So it is 0 plus 1 over square root 2, just to understand what's going on. Here to trace the qubits on the simulator, I just point here and click on the probability. So the figure here will show the probabilities of the unknown qubit. If I stop here and click here, it will show the probability of the auxiliary qubit. So let's see what will happen on the auxiliary qubit. So if I move here, this is the unknown qubit. Ignore gate 1 because it's supposed to be unknown. Now, when we apply this gate, actually some entanglement happens between, but not fully entanglement. Weakly entangled happens between the unknown and the auxiliary. And actually, I will apply sharp measurement at the end of the day. So I want the probability of AX. The idea is to make the probability of AX, the auxiliary qubit, as close as possible to half. So it will be 50-50 to be 0 or 1, so that we will allow the probabilities of the unknown qubit to influence the probabilities of AX. So let's see what will happen now. I will apply this sequence of gates. This sequence of gates are carefully calculated, and now it is 0 and 1. If you apply sharp measurements, it will collapse to 0 or 1. So what happens on the unknown qubit? Let's see what happens if I keep my eye on the unknown qubit itself. So again, I reset. I will repeat everything again. So here, the entangled, and I will prepare this part to make the probability of the auxiliary qubit 50-50, or as close as possible to 50-50. And now when I apply sharp measurement here, what will happen on the auxiliary, on the unknown qubit itself? So some disturbance will happen. Okay, the good thing that if we repeat this, and if we get 1 times 0 and 1 times 1, this will be reversed. Again, more disturbance happen. Let's go faster. This is probabilistic anyway. Okay, now it is going back. It is restoring its probability. So some disturbance happen here, but if you get, I will show this in equations in a minute. If we get equal zeros and ones on the auxiliary qubit, actually the amplitudes of the unknown qubit will be restored. So no disturbance happen on the auxiliary qubit. So the main idea is to count these ones and zeros as follows. So this is equation to show the updates during happened on the unknown qubit by applying successive measurement on the auxiliary qubit. This is a closed form of the system. Let's ignore it for now. But the interesting thing now is that actually the probabilities of the unknown qubit will move up and down based on the sharp measurement on the auxiliary qubit. And this actually very similar to the random walk. Actually, the rule of the mu, the free parameter now, is to adjust the strength of the weak measurement on the unknown qubit. So if we make mu very small, the measurement, the disturbance will be very high on the unknown qubit. And if we make mu very large, so the disturbance will be very small. what we are going to do, we are going to count the outcomes of the sharp measurement from the auxiliary, not from the unknown qubit. Let me show you a very short video about this random walk because I believe it is very interesting. So here mu equal 1, the measurement is very sharp. And remember that here we found 0, we found 1, we found 0, we found 1, and so on. Here the disturbance mu is very small, the disturbance is very high. We are really changing the amplitudes of the unknown qubits. But in a minute, after these few runs, we will show mu, if we make mu, these three parameters, very high. What will be the effect on the unknown qubits? So again, here the disturbance is very high. We don't want this to happen because it will disturb the unknown qubit we are trying to read. Actually, as I said, random walk itself, instead away from reading the content of the qubit, random walk itself, or let's call it quantum random walk itself, has many applications. Now we make mu very high. You can see that actually the disturbance is very weak. The changing up or down becomes weaker than using mu equal 1. And this is another random walk. So this system, if someone is interested in random walks and the simulations of, because random walks actually, as I said, has many applications. So what's the aim of what we are doing, what we are trying to say? First, we want to make the measurement on the auxiliary qubit has weak effect on the unknown qubit. So no disturbance, or at least very small disturbance, happens to the unknown qubit. To do this, we actually can make the root of the partial negation greater than the d. Why is this? For not making full negation. Full negation means full entanglement. Full entanglement means if I apply measurement on the auxiliary, it will directly affect the unknown. But I don't want this. So as long as the negation is smaller than the D1, it will always be weak entanglement, so measurement will not affect the unknown qubit. Another thing we want to achieve is that to prove that actually weak measurement can be reversed. So it is a reversible operation, not a reversible operation. Another aim is to read the content of the qubit itself using this counter. This is the only thing we can watch from outside the system, the counter of the measurement on the auxiliary, not the unknown. Again, I showed you that we can do this. We can make the probability of AX close to 0, and this is the rule of the mu. Why we want to do this? So that the impact of the unknown value of the amplitude of the unknown qubit appears on the probability of AX. We can actually make this balance, this 50-50, by adjusting these parameters. So if you want to use mu, for example, 10, you have to adjust C, the root of the partial negation, to this formula. This will ensure that always the probability of AX, the auxiliary qubit, very close to 250. So how can we prove that actually what we are trying to prove here is reversible? Again, remember that J0 is a probability, is the number of counts that we found AX equals 0, and J1 is the number of counts equal to 1. Actually, these are proved here. I will just jump to the results. We proved that actually if at any moment of this random walk, if J0 equals J1, actually the system will be restored to the original amplitude. So actually, at any point when you count J0 and J1, you will find if they are equal, so nothing happened, nothing disturbed on the unknown qubit. So this is very important to the algorithm. But actually, this is a random walk. So random walk can go in a wrong directions or go in a correct directions. It is a random walk. So we showed that actually how far the random walk will not introduce much disturbance on the qubit we are trying to read. So if it moves in the correct direction, so this is fine. If it goes in the correct direction, in the wrong direction, so something wrong happened. What I mean by correct, move in correct direction or move in wrong direction. Actually, if the probabilities of the zero state of the unknown qubit is higher than the probability of the one state, we expect that the counter of J0 will be higher. And if probability of 1 is higher, so we expect the outcomes as 1 on the auxiliary qubit to be higher. So what happens if we find something else? As long as it moves in the correct direction, so nothing happened to the qubits. So this stability of the algorithm shows that actually if you go for delta J steps in the wrong direction, delta J here is the difference between the counts, not the number of random walks, but actually the difference between them. So actually if we go for delta J in the wrong direction, I will assume that actually the system went in the wrong direction. So we proved here actually as long as the difference between the counter for the 0 state and for the 1 state did not succeed this value, so we are safe. We are still can recover. We can restore the amplitudes of the unknown qubits. Again, the strength of the measurement can be controlled, as I said, using this mu operation. So if we make mu very small, so the strength of the weak measurement will be very high. And if we make mu very large, so the strength will be very small and no disturbance will be allowed. This shows that actually this process we are trying to, we are showing will converge to the sharp measurement after all. This is bad news, right? So how far we have to go in the random walk before we converge to the sharp measurement. So actually we can do this for mu square iterations. So mu square iterations is the long. After mu square iterations, actually the random walk will not go up and down, but it will collapse to 0 as a sharp measurement, or will collapse to 1 as a sharp measurement. So we have to stop before this mu iterations, mu square iterations, for not disturbing or for not breaking the superposition of the unknown qubits. Actually, this simulation shows that the theoretical equations is similar to the simulations, because actually this is the average of random walks, and the blue line here shows that what we can gain from direct measurement on the unknown qubit. And this green is the result of the random walks, the count between 0 and 1. How far, for example, if you have probability of 0 greater than probability of 1, you expect that counter 0 counter will be higher than counter 1, and vice versa. So this is a sharp, and this is a simulation using random walks, and actually it matches with very good accuracy, that actually we can guess the information in the qubit using the counting the outcomes from the auxiliary qubit. In another research, recent research, maybe it is on the archive, maybe a couple of weeks now, we studied the quantum state discrimination using this algorithm. Quantum state discrimination is very important in quantum key distribution, for example, BB84, which depends that actually we cannot discriminate between 0, 1 as a computational basis, plus minus in the Hadamard basis, and the security of the protocol, the quantum key distribution protocol, depends that we have always 50-50 probability to distinguish between 0, plus, 1, and minus. So we try to test what will happen if we want to read this content without disturbance using only single qubit, because quantum key distribution usually implemented on trains. So you send trains of photons polarized according to the code you are trying to send. But we challenge ourselves in this, that we actually have only one copy of the qubit in this quantum key distribution. So actually we realized that we have equivalent behavior between behavior in the random walk between this 0 and plus, and you can see 1 and minus. This is sample random walks. If we start with 1, if we start with 0. So the challenge now is how can we discriminate? We can now distinguish between 0 plus as a type, because the random walk always ends up, and between 1 and minus, because random walks always ends down. So the challenge now is how can be distinguished between 0 plus and 1 minus. So we start analyzing the ones, the trains of ones and zeros from the sharp measurement on the auxiliary qubit, and we modified the algorithm a little bit for the quantum state discrimination algorithm, and we added this part. First of all, we don't know if the qubit in state 0, state 1, state plus, or state minus. So based on these outcomes, we took a decision after very few iterations. If we will go, the random walk will go as usual, and then we will assume that the basis will be 0 or 1, or because it starts if it is plus or minus, the random walk will start from half, 50-50. So the up and down will be almost equal. So we decide to apply H. If we decide to apply H, then we make decision that it is in the Hadamard basis. If we did not apply H on the unknown qubit, then we assume that it is on the computational base, the normal computational base 0 or 1. And we go on and we keep counting, and that's it. The results actually are surprising, because here now, if I say the unknown qubit is 0 or 1, now I did not apply Hadamard to change the basis during the random walk. So I now took my decision that they are in the computational basis. If I apply Hadamard during the random walk, then I took my decision that it is plus or minus. And actually, the random walk shows that you can see from the figure that actually 75% we can take 75% to be correct, 75% instead of 50-50. The original result, the original security of the quantum key distribution, it is 50-50. But actually now we have 75% to get the correct information in a qubit, to the correct basis of the qubit, and this is somehow breaks the random guess in the encoding. Actually, this is not new. This result is not new. The theoretical upper bound on this has been proved theoretically from a while, but we did not find any quantum algorithm or quantum circuit that can be implemented to get this result. So this result means that we have to be careful with the quantum key distribution. The last thing before I finish my talk and receive questions from your side, to show you another very interesting application of this random walk. We are working on it right now, which we are trying to use this random walk as an amplitude amplification technique. The random walk here, before I start this video to show you the behavior of this random walk, we are trying to amplify the amplitudes. It is similar to amplitude amplification, not similar as a job, not as a technique, like Grover's algorithm. We are trying to find solution using amplitude amplification. The interesting part here in this random walk is that the probability to go up and down are not equal. So it is not moving in a homogeneous or 50-50% like in the other walk, but actually using partial negations, again, we artificially trying to make the probability of AX very high. So here it is trying to amplify, but actually it falls down very quickly. This works still under progress. But actually the random walk itself is very interesting because it is not, if we call the normal random walk is the drunk man walk, this walk we can call it standing up random walk, as if the probability is trying to stand up, but sometimes it falls down. So here this standing up man could not make it. This is another one. He is trying to go up, but he falls. He keeps trying. Actually, it's inspiring. This is one of my favorite random walks. He's trying to stand up, go up. As here, he is almost succeeded, reached to the probability 1, and okay, that's it. He's very good. This is another one, but he is trying to stand up again. Let's see what happened. The strange thing in this random walk, actually, when it goes down very fast. So it increases gradually, but it goes down very fast. Here, he could not stand up, and he dies. Here, let's see if he can make it. He is working hard. So we are trying here to give this standing up man a hand, so he can always can stand up successfully. Okay, he is almost done. This is another one. Maybe the last one. So he's doing well here, but unfortunately he falls and he keep trying to stand up. And actually he did it after all. That's it. Actually, this is my talk. This is a reference for the original paper in 2017, reading single qubit, and this is a recent paper for quantum state discrimination. And I would like to thank you again, and I'm happy to receive questions.
Okay, great. Thank you, Professor. Actually, there are some questions on our chat. Mostly there are questions about the tool, the simulator that you used. I guess that the name is Javantum. Is this correct?
Javantum is our simulator. It is available on our website. I will send you the link. Okay. But the original simulator, I have to copyright the original simulator. It's called Jacuzzi. It is very useful, handy, especially in lectures. So it is very useful. I recommend people to use it. So I will send you the link of the Javantum.
All right, great.
The link of the original simulator, the Jacuzzi simulator.
Okay. So yes, great. Yeah. You can just
show post, you in a minute. Yes.
Yes, you can post the link on the chat. So where these tools somehow integrated. So because there was a question about the backend. So I guess that the simulator was a backend for Javantum. Is this correct? Or
yes, Javantum, because it's built on Java. Actually, it is a graduation project with our undergraduate students. I will send you the
okay,
the link here.
great. And in the meanwhile, Przemek from our student association, one of our partners, has posted a link to a Google form. If you want to obtain a certificate of attendance, then you can just fill in
Okay.
this short form, of course. So
Yeah,
this is just a question to participants, but yeah, we are looking forward. Yeah, so we can now see the link.
Yeah, actually, I send you this.
Yes,
You
great.
can find two simulators. The first one, Alex Qubit, is still under development, but Javantum is fully functioning. It is in the and the link for the original Jacuzzi simulator in the page 2.
Great, fantastic. All right. Are there any more questions? Currently, I don't see more questions on our chat, but actually, I have one question. Yeah, that was very interesting and an interesting logic gate, new logic gate for this partial negation. Can you see that there might be? Do you know how to build a physical representation of such a partial negation? I mean, do you think that, because currently the experiments were run on a simulator, but do you think that it will be easy or rather difficult to build such a quantum logic gate?
Actually, this gate is now on IBM,
Right.
IBM quantum computer. This nth root of knot is on IBM. They added it recently. I hope they added it because of this paper. I don't know, but I didn't see this operator anywhere else. So I hope they saw it in our paper. So actually, we are working now to implement this algorithm or this technique on IBM directly. They have now this nth root or C's root operator.
Great.
And actually, one very interesting thing is that we can do some tricks using partial negation. Partial negation is actually a very trivial operator, but it turns out to be very useful after all. So we are working in another direction. What we will get from C's root of Hadamard, for example, or C's root of Z, or C's root of Pauli Y. I believe more interesting results can be done in this direction.
All right, very, very interesting. So I hope that IBM will acknowledge your work at some point. If it was really an inspiration for them. Okay, yeah, I can see that Karim Al-Safti, our previous speaker, has joined. Hello, Karim. So maybe if you have some interesting questions or not, is Karim also involved in this project, or I was just wondering. But anyway, there is another question on our chat. What happens for multiple measurements? Yes, there is over zero. For example, mu control the disturbance, and if a little disturbance took place every time, what happens for a second measurement or a third one?
Actually, this is what we showed in the reversibility of the operator. So I'll show you a random walk in a minute. So this slide shows that actually this weak measurement is reversible. So every time you find J0 equal J1, the amplitudes are actually stored. So what we mean by J0 equal J1, let's go back to this random walk. So for example, it's something like this. Here we found 0. Again, we found 1, we found 0, we found 1. So as long as the number of zeros equals the number of ones, or no disturbance actually happened on the unknown qubits. So I hope I answered the question.
Great, thanks. Yeah, Saha has just replied that Yeah, I see. Thanks a lot. So it looks that this is a sufficient answer. So thanks for this. All right. I don't see more questions now on our chat. Or are there any more questions? I think this is the last opportunity to ask some questions. Okay. So maybe just one last question. So you said that you are also thinking about this C root operators for some other gates. So is this the main research directions in your research direction in this area, or are there some other interesting research topics to which maybe potentially some of our members can join, or do you know if there are some other people around the world working on these topics, or is it developed only in Alexandria in your research group?
Actually, this direction, I believe it started in Alexandria, but this is not my only research area, because mainly my work was on developing quantum amplitude amplification techniques. That's why it started, because I was trying to develop an amplitude amplification techniques, but actually till now I did not finish this. But this random walk appears, and reading the single qubit appear, and this quantum state discrimination appear. But actually, the standing up random walk did not appear yet. So it is on the direction of amplitude amplification techniques and quantum algorithms.
All right, great.
But we saw that it may be fruitful, so we focus on this right now.
Mm-hmm. Great, fantastic. All right, I don't see more questions on our chat, so I think we can finish for today. So maybe just let me share my slides again.
Okay, I'll stop my share now.
Great. All right. Yeah, let me just share again. Okay. Yeah, so I just wanted to let you know that our next meeting will happen most likely on 10th of May. So there will be announcements soon. We expect to have speakers, guests from D-Wave. And yeah, we would like to thank once again our strategic partners and honorary patrons for supporting us, and we hope to see you and meet you next time.